remember when I lost my mind.
Okay, this is topic number 7, waves. This topic talks all about really the transfer of energy. That's what waves do. Waves are a means to transfer energy from one place to another. So, you know, when you have someone talking to you, you're listening to me right now, either through headphones or from the computer. The air particles between you and the computer are being moved back and forth, but the energy is originating from the speaker, and it's actually making your eardrums move. So there's actually a transfer of motion energy, kinetic energy, from the speaker to your ears. These pictures we'll look at in class. Now, some definitions of waves. This is essentially what the waves topic's all about, is the basic understanding of waves. So if we're looking at the first type of waves, transverse waves, we'll look at some examples in a minute. Essentially it's a wave. If you have a look here, you can see the, if you had a cork on top of this thing here, okay, the cork's motion would be up and down. Okay, so up and down is the motion of it. However, if the thing creating the waves was some sort of machine bobbing up and down, okay, so making the waves, and at this end you then had in a cork, this thing will start bobbing up and down, so we've transferred energy across this way. So a transverse wave is the particles move at right angles, so up and down like that at right angles, and the actual motion is perpendicular to that, okay, and it's straight across. So here's an example of transverse wave in animation here. So you can see the energy is sort of flowing across. You can see it drifting across over time, but the particles themselves, if you look at one particle, it's just going up and down on the same spot. This is another example. Let's get rid of that. Try again. There we go. And so you can see the particles are just going up and down, but the energy direction is across. So what's some examples of that? Well, usually you'd say the water waves, but generally it's only the surface of the water waves, okay? Even then, it's only just acting like a transverse wave. But the main one here is that all electromagnetic waves are transverse. I should really use a nicer pen. So all electromagnetic waves are transverse, and there's also a type of earthquake wave, which is the S wave. You can think about it. The other one's a P wave, but you can remember an S wave is transverse because of the shape of the S. It looks like a transverse wave. So S wave, so that's from an earthquake. Okay, so there's three sort of types there. Electromagnetic, I mean, obviously that one covers visible light, microwaves. There's a whole lot of different types there. Longitudinal is a wave in which the displacements of the particles in the wave are on the direction of transfer of energy of the wave. So direction of travel, or energy, in this case, is that way. So going along. However, the particles also go in that same direction. So the particles, this particle here, will travel this way and then travel that way from a mean position. Okay, so the oscillation is back and forth over time. And you can see here where the particles have the greatest gap. So where there's the greatest gap, we have a refraction, okay? And where there's the smallest gap, we have a compression. Something else to remember too is the greatest pressure will be high at a compression and low at a rarefaction. So here's an example of a longitudinal wave. So you can see here there's some sort of bar oscillating back and forth. Okay, and if we look at one of these dots, you can see it just stays where it is. You can see the general trend. Looks like it travels right along. Okay, but that's just the energy. The particles themselves just oscillate around one spot. So if we choose a spot, let's say that little dot there, you can see the, let's make it a little bit bigger. So you can actually see the particles just going back and forth right beside it. They're not actually traveling along from one end to the other. Here's a little diagram of this. Oh, another little dot. Oh, annoying. There we go. You can see the particles stay where they are on average, but they move back and forth. What's some examples of that? Okay, well, sound is the main one. So sound is the main one. Okay. Ultrasound you can see there, but that's essentially just sound. Okay, that's how we get this image here. The compressions or refractions will come in, bounce off the baby and back out again, and you can measure distances, and so you know what's there. We look at that more in A2 physics. What else? There's an earthquake wave, which is the P wave. Primary, okay, and that's from the earthquake. That's about it for longitudinal waves. So looking at some wave terminology, displacement is your displacement from the mean position of the particle. So let's say we're looking at a transverse wave like this. Okay, there's the mean position along there. Okay, and the height up and down is your displacement, okay, from this mean position. So if we're looking at that point there, it might be 1 meter. That is your displacement, okay. So amplitude, on the other hand, if we graphed amplitude, then if we graphed, let's say, or looked at a transverse wave, then amplitude is from the mean position, okay, or rest position, to the maximum displacement. Now you should use the dictionary to find the meanings of all these, okay? Just another note on displacement. If it was a longitudinal wave, let's say we had some particles like this, and they compress, and then they refract, and then compress, okay? If we knew that the mean position of this particle number 1 was there, then the distance changed, okay? S will be the displacement. Okay, so how far horizontally from the mean position for longitudinal, how far up and down from the mean position for transverse. Wavelength, the shortest distance between 2 points on a progressive wave which are vibrating in phase. Okay, or another way of looking at it is if I look at this position here, the wavelength is the distance to the next position in the same motion. It can't be that one, okay, because it is, the particle is moving, if there's a particle there, is moving in an opposite direction. So the next position is there. So that is a wavelength as well. Okay. Once we look at phase later on, you might understand what it means. But essentially phase is the motion of the particle at that time. So if the things are in phase, then they're doing the same motion. Symbol, lambda. Unit, it's in meters, it's a distance. Period, the time taken to complete one oscillation in a vibrating system. Okay, so if you had a stopwatch, or like an alien. That's my stopwatch. Okay, and if you time a wave flowing past you, so you're standing here, so you're timing it, when does it go past that point? The wave could be traveling this direction, so you'll start the timer maybe when it reaches the crest, okay, and then when the next crest passes, you then stop the stopwatch, okay, and that's your period. So what's the symbol? Capital T, symbol small s. Frequency is the number of oscillations per unit time. So before, for period, we measured the time for one oscillation there. Okay, how long did it take for that one oscillation to pass? Well, in this case, the timer is going to just time 1 second, and he's going to count how many crests go past. So if it's 2 crests in that 1 second, then we have 2 hertz. Okay, so frequency is sort of the opposite of period. Symbol for frequency, F, okay, unit, hertz. Oh, did I do the unit symbol in unit? Yes, I did. Okay, good. So, frequency and period are related how? Well, essentially I just said they're the opposite. So frequency could be related to the period by 1 divided by the period, or period could be equal to 1 divided by the frequency. Speed is the speed at which the wave's energy is propagated along. Okay, what's that measured? Well, it's just the normal velocity in meters per second. Sometimes with waves, C can be used. Okay, so whenever you think, i.e., think of this equation, E equals mc squared, there's your constant for speed of light. This is what we're going to discuss in class, and I might get you to write something on the survey about this, but speed of light, velocity of light, just have a think about what they mean in terms of vectors. Finding the speed of a wave, okay? Speed is a distance we've defined already as the wavelength. So speed, remember, is distance over time, okay? A distance we have defined, so we're looking for this value here in terms of a wave, and in this case, we've used wavelength already, okay? And it's measured in meters. We also know a time it takes for this one wavelength. So how long does it take for one wavelength to pass you? Okay, this is the period. So we're putting that in there. Okay, and so if we substitute these values into the equation, we get V equals your distance measurement and the time for that distance measurement. But we also know that period is equal to 1 over the frequency. Okay, so if I substitute 1 over frequency into there for the period, I will get V equals F lambda, which is a more common way that we use a formula. But remember, there is 2 formulas here. So a wave has a frequency of 25 hertz and a wavelength of 1.2 meters. What is the speed of the waves? Remember doing V equals, well, what do you got here? Okay, frequency, wavelength. So frequency, remember, is F, wavelength is lambda, so the equation must be that. And I'd like you to finish that. Wave has a speed of 300 meters per second and wavelength of 2 meters. What is the frequency and the period of the wave? So we're trying to find both. Okay, well, we know from a formula that we've got velocity here, or speed, and the wavelength lambda. So we could find either frequency or the period. Frequency is equal to V over lambda. So it'll be 300 divided by 2, so that equals 150 hertz. What's the period? Well, we know that it's the inverse of frequency. Here's a common exam question. Okay, the displacement shows, the diagram shows a displacement time graph for a wave. Okay, so that's quite important. Displacement time, okay, for a wave. What are the amplitude and the frequency of the wave? So the amplitude, remember, From the mean position to the maximum displacement is your amplitude. So in this case it's 4, so it's either one of those two. What's its frequency? Remember, frequency is equal to 1 over period. Why do I use that formula? Because I'm given a time, and time is related to period, not frequency. Something to be aware of is that value there, milliseconds. So what is the period? Well, it's a time for one complete oscillation. That's one complete oscillation there. Let's just do that in a different color so you can see it. There you go. It's one oscillation there. How long is that? That is 20 milliseconds. Okay, so put that in there and you get an answer. Put the answer in the survey. Diagram shows a transverse wave on a rope. The rope is traveling from left to right. At the instant shown, the points P and Q on the rope have 0 displacement and maximum displacement respectively. Which of the following describes the direction of motion, if any, of the points P and Q at this instant? Okay, just have a think about this. The direction is going this way. So if you imagine watching the surface of the water, you'll see this crest here will, in the future, be over here. So in the future, the whole wave will move across to the right. Okay, so where will Q be? Q's gone to there, okay, in the future. But am I actually going to move Q? No. The Q is not moving that way. The Q is going to stay in this column. So imagine it's like a little cork, okay, on the surface. This is the future here of where it's going to be. So the point Q will end up down there. Does that make sense? I hope. So at this instant, though, it's just moved up, okay, and then it's going to come back down. So we're actually changing direction. So what's the motion of Q at that time? Well, it's actually stationary. So it's either that one or that one. What's P doing? Well, P has not just changed direction, so it's not stationary. It's not like projectile motion. At the top, you are stationary, okay? The top B is stationary. In this case, we are halfway down our fall. So that means we are falling down, and in the future, it's going to end up down there. So it's actually falling downwards. A. Drawing a longitudinal wave. Okay, this is just out of interest that it's too hard to draw these sort of things. Okay, that's like a spring there. We'll do that in class. So instead what you do is you look at where the compressions are and you draw a crest. Okay, so compression, compression, compression. Those are the crests. Refractions are your troughs. Okay, and that way you can then make it look like a transverse wave diagram. Okay, a displacement distance graph of a wave. Okay, so what we've got here is displacement and we have distance. Okay, so this could be distance in meters and this could be S in meters. So what can you get from it? You get the wavelength when you're going crest to crest. Okay, it's very important to notice that. If you have a displacement time graph, so in other words it might be S meters, and this could be time seconds, then we can measure the period for one oscillation. And it says here a point, okay? So this is actually just watching a point go up and down, up and down, up and down over time. So you imagine you're dragging a sheet of paper past that point. So you're dragging the paper along this way, and then it'll just leave a trail as you drag it along. Okay, so we're looking at just the one point. Waterways, we talked about waterways. The surface of waterways can almost be modeled as a transverse wave, but really there's something called Rayleigh waves. They travel around in circles. Okay, so the particles in the wave travel in a circular fashion. And you can almost see that. If the wave was getting shallow like here, it could still go around here. It's getting pushed up more vertical. It's running out of room. There's a point here where as it goes around, there's actually not enough water to continue the motion, and that's when you start getting the sort of the barrel effect going. There's not enough water to be drawn back to keep the thing solid. Okay, so that will do for the video number 1.
I remember when I lost my